Welcome to this video. So in today's video, we'll be looking at tutorial sheet 1, and this is chemistry for students at Apex University. Okay, so this tutorial sheet is on questions on units and measurements, and we're going to solve all of them here. Okay, so I'll be explaining the concepts when we are solving each of these questions here. Okay, so I hope you enjoy it and you learn something from whatever I'll be explaining. All right, so let's start from question 1 there. So question 1, they're saying evaluate the following. Okay, so here they just want us to divide two numbers that have different number of significant figures. So we can see we have 2.34 times 10 to the power minus 7 nanometers divided by 1.6754 times 10 to the power minus 18 nanometers. Okay, so for you to answer this question, you have to know the rule, okay, that governs the division of two numbers that have different significant figures. Okay, so the rule when we are multiplying or dividing two numbers that have different number of significant figures is that, okay, the answer that you're going to get should have the same number of significant figures as the number that had the least number of significant figures of the two numbers that you are dividing. Okay, so you can see this number here. Okay, I'll write it here, 2.34 times 10 to the power minus 7 nanometers. Okay, so this number here, how many significant figures does it have? Okay, so we can see that all the numbers here are just non-zero numbers. So it means it has 1, 2, 3. Okay, so there are three significant figures here. So we'll write here three significant figures. And then what about this number, which is dividing here? Okay, so we see that number is 1.6754 multiplied by 10 to the power minus 18 nanometers. Okay, so how many significant figures does this one have? So it has 1, 2, 3, 4, 5. Okay, so it has 5 significant figures. So the rule when you're dividing or when you're multiplying is that the answer that we are going to get after we divide this, okay, should have the same number of significant figures as the number that had the least. Okay, so the number that had the least here had three significant figures. So it means that our answer should have what? Three significant figures. Okay, so the rest now is just to divide since we've known the rule. Okay, so this slash here, this slash here simply means division. So here, if I can write it in this form, it is 2.34 multiplied by 10 to the power minus 7 divided by, okay, so don't forget the units, divided by 1.6754 multiplied by 10 to the power minus 18 nanometers. Okay, so here what we are going to do is that we are going to separate this number into two. We're going to separate it into this part, okay, and then these ones here that have 10 to the power something here, we're going to put them together as well. So we are going to write it as 2.34 divided by 1.6754 and then multiplied by 10 to the power minus 7 divided by 10 to the power minus 18, and then we say nanometers. Okay, so this is what we have. So from here now, we're just going to punch the calculator to get the values of this part here. And then here, we're just going to use laws of indices. Okay, so when we do 2.34, okay, 2.34 divided by 1.6754, okay, what do I get? I get 1.39668139, okay, when I divide this, and then I'm going to say multiplied by, and then here we're going to use laws of indices. Since here I have a 10 and there I have a 10, okay, and I'm dividing this, I'm going to subtract their powers. So I'm going to say this here is the same as 10 to the power minus 7 minus, and then in the brackets we put minus 18 like that. Okay, so this is going to be equals to 10, okay, It's going to be equals to 10. There it's going to be minus 7, and then negative multiplied by a negative. It's going to give me what? It's going to give me plus 18. Okay, so minus 7 plus 18. What does that give me? So this is 18 minus 7. That will just give me a positive 11. Okay, so here, this part here becomes 10 to the power what? 11, and then we say nanometers. Okay, so what is left here now is determining the correct number of significant figures that this number here should have. So we determined that this one had 3 significant figures. This one had what? 5 significant figures. So we have to round off this number here to how many significant figures? 3. Okay, so we'll come and round it off from here. So we'll round off this 6 to that. Okay, so if this number is 5 or greater than 5, then we add a 1 to this one. Okay, but when we add a 1 to this one becomes 10. Okay, so we take the 1 to the 3, and then this one remains 0. So it means our number will be 1.40 times 10 to the power 11, and then this will be in nanometers. Okay, so this will be nanometers. So this one here will be our final answer when we divide these two numbers here. Okay, because this one here has 3 significant figures based on the rules that we learned. We said if there's a decimal point here, then a trailing 0 becomes significant. So we have 1, 2, 3, just like the number that had the least number of what? Significant figures. Okay, so this is the correct answer here on A. All right, let's look at B. So B, there's a combination of operations there. There's a subtraction there, and then there's a division, okay? So the rule when you're subtracting or when you're adding is that the answer should have the same number of decimal places as the number that had what? The least number of decimal places. So for example, if I'm adding 1.0, okay, to 7.001, when I add these, okay, I'm going to get 8.001. Okay, so this answer here, when I'm adding or subtracting, should have the same number of decimal places as the number that had the least. So this one here has how many decimal points? 1. This one has 1, 2, 3. So it means the answer there should also have 1. Okay, so this would be 8.0, just like this. Okay, so when you are subtracting or adding, you are looking at the number of decimal points. Okay, number of decimal points or places. And then when you're multiplying or dividing, you're looking at the number of significant figures. Okay, so don't confuse the two. When you're subtracting, adding, number of decimal places, multiplying, dividing, number of what? Significant figures. Okay, so here there's a mixture. We can see on top there we have a subtraction sign, and then we are dividing whatever we are going to get from there. We are dividing it by another number. So we have 1.00 meters minus 0.500 meters. Okay, and then divided by 0.50 meters. Okay, so when you look at this number here, that's 2 decimal places. Okay, and then here, I think I wrote an extra 0 here. Okay, so it's just 0.50 meters like this. So this one also has how many decimal places? There's 2 decimal places. Okay, so when we subtract, the answer that we should get should have two decimal places as well. So this is going to be equals to, so 1.00 minus 0.50, okay, it's going to be 0.50 meters. So divided by 0.50 meters. Okay, so now here, that's where the trick is, because most of you just divide this and then you are going to say my answer is 1 meters. Okay, but here, this 1 meter here is not the correct answer. Why? Because we are considering the what? The number of significant figures. So this one on top here, since now we are dividing, here we were adding, so we are considering decimal places. But here now we are what? Dividing. So we are considering number of significant figures. So the number on top here, it has how many significant figures? Okay, it has 2. It has the 5 and the 0. So this 0 is significant because it's a trailing 0 and the there's the presence of a decimal point there. So this one has two significant figures. Even the one down there, there's two significant figures. So when I divide these two, the number that I should get, okay, the number that I should get should also have two significant figures. Okay, so when I divide this, I'm just going to get 1. Okay, but how do I make 1 to have two significant figures? I'm just going to write 0.0 like that. Okay, and then I write meters. So this one here has 1, 2 significant figures. Okay, so the answer here is 1.0. Okay, the answer there is 1.0 meters. So we are done with question 1. We've solved A and B. Let's go to question 2. So question 2, we are converting units. Okay, so if you've been watching my videos, you know that there's an easier way to convert this. Okay, and then here we're going to use dimensional analysis because we have 2 units involved. Okay, so the first one, we are going to say this is 3.9 milligrams, and then we want to convert this to nanograms like that. Okay, so there's a very simple method that we use here. Okay, it's called the metric system method. So you have to know the meaning, okay, the meaning and the symbols of a metric system. So this M here, it has a meaning. This N here, it has a meaning. And then this G and this G, those are just grams. Okay, those are just grams. So this one here, the M and the N, they are what we call as prefixes. Okay, so this is a prefix, even this one is a prefix. So whenever you see a prefix, it has a value attached to it from the metric system or from the metric table. Okay, so this is 3.9 milligrams. We want to take it to nanograms. So the M here, the small letter M, means milli. So you can see it there. Okay, there's this M here, it's meaning it's milli, and then it has a value which is 10 to the power minus 3. Okay, and then the nano is this one here, like a small n. You can see nano, and it also has the value attached. Okay, so when you're converting units from one submultiple of 10 to another, just use the metric system. So to convert this from milligrams to nanograms, I'm going to say this is 3.9 times, okay, what is the value of a milli according to the metric system? Okay, so according to the metric system, we're told milli is 10 to the power minus 3. So I'm going to say 10 to the power minus 3, and then divide it by the prefix of where you are going. So we are moving from milligrams to nanograms. Okay, so I multiply by the milli, I divide by the nano where I'm going. So the nano has 10 to the power minus 9. So I'll divide this whole thing here by 10 to the power minus 9. Okay, and then I can write this as 3.9 over 1 multiplied by 10 to the power minus 3 over 10 to the power minus 9. This is the same because when I multiply this multiplied by this, I get whatever is on top there. Okay, 1 multiplied by this, I just get what is down there. Okay, so it means here I'll still remain with 3.9. Okay, and then I say times. Here I have 10 to the power minus 3, 10 to the power minus 9. So I can combine this. Okay, so I just say the base is the same there. So since I'm dividing, I can subtract the powers. So it will be 10 to the power minus 3 minus 9. Okay, so remember to put the minus 9 in brackets like this. So this will just be what? Okay, it will just be 10 minus 3 plus 9, okay, which is 10 to the power what? 6, like this. So I'm going to multiply 10 to the power 6. Okay, so this is now in nanograms. So we have converted from nanogram to what? I mean from milligram to nanogram. So that's how you do it. Okay. Okay, and then let's say we were asked to do the opposite. Okay, we'll still get back the answer that we started with. Yes, okay. Let's say, for example, we are converting now from nanogram to milligram. Okay, so the only thing that I need to do is write 3.9 times 10 to the power 6 multiplied by the value of the nanogram, because now I'm coming from the nanogram to the mid. Okay, so the one you're coming from, you multiply. Where you're going, you divide. So nano 10 to the power minus 9. And then I said divided by 10 to the power minus what? 3 for the mid, this one here. We want to see if I'm still going to get this guy here. Okay, so what I'm going to say here is just 3.9 times. So this is 10 to the power 6, 10 to the power minus 9. So since here we are multiplying, we can add the powers. Okay, so this will be 10, 6, and then plus minus 9, which is the same as 10, 6 minus 9, which is the same as um, 10 to the power minus 3, right? Okay, so on top, this one and this one have combined. They are now 10 to the power minus 3. Then I'm dividing all this by 10 to the power minus 3. So this is going to give me 3.9 times 10 to the power minus 3 over 10 to the power minus 3. And then here we can apply the same rule. Okay, but since we are dividing, we're going to subtract the powers. So we're going to get 10 to the power minus 3 minus 3, which is just 10 to the power minus 3 plus 3. So minus 3 plus 3, that is 10 to the power 0, which is just 1. So I'm just multiplying this 3.9 by 1, okay? And then since I'm converting from nanogram to milligram, that becomes my milligram. So you see how to convert, right? Okay, so as long as it's just a sub-multiple, okay, but you are converting within the same units, because here we're at grams and grams, then you can use the metric system to convert. So you just have to know the value of the milli, the nano, or whatever you've been given here, and then you use it to what? To convert. Okay, so let me do another example just for your understanding. Okay, so let's say I have 2.51. Okay, let's say this is pico. Okay, so this is pico meters, and then I want to convert it to let's say I want to convert it to uh centimeters, like this. Okay, so the only thing that you need for you to convert from picometers to centimeters is to know the value of the pico and the value of the what? The centi. So we're going to say this is 2.51 times, what is the value of the pico? So you go to your metric system. So the pico is down there. So this is 10 to the power minus 12. So it will be 10 to the power minus 12. And then I'm dividing all this by the value of the centi. So centi is this one here, which is 10 to the power minus 2. So this will be 10 to the power minus 2. So this is going to give me 2.51. Okay. And then I'll say times. And then here, this is 10 and 10. So I can do that trick, right? I can say 10 to the power minus 12 minus 2, since this one is in the denominator. So I'm dividing these two here. So that will just be 10 minus 12 plus 2, which is just 10 minus 10. So this will be 10 minus 10 centimeters. Okay, so 2.51 picometers is the same as 2.51 picometers is the same as 2.51 times 10 to the power minus 10 centimeters. Okay, so that's how you can convert using the metric system. Okay, so if you missed the video that we did this, okay, you can just search it on my YouTube channel. Just search converting units to tuple solutions. It's going to come. Okay, it's going to come. So you can watch the full video where we're doing our questions on converting these units. So now let's convert B, where we have dimension analysis. Okay, so dimension analysis, when you go to physics, okay, Tutor John will tell you that dimension analysis will be used to check the consistency of the formula. Okay, but in chemistry, when we're using dimension analysis, it just means we are converting units that involves 2 units, but in one question. Okay, so you can see this is centimeter per second, and then we are converting this to meters per hour. So we are converting 2 units at once. So we use dimension analysis. Okay, so B, we have 100 centimeters per second. So 100 centimeters per second is the same as 100 centimeters divided by 1 second. Okay, so this one is the same as this. So I want to convert this now to meters per hour, or we want to convert it to meters over what? Hour. So what are we going to do? We are going to say 100 centimeters divided by 1 second, okay, and then multiply by, so we are going to multiply by what we call as conversion factors, okay? So when I look at the distance, I have a centimeter that I want to take to a meter, okay? So there I have to know that 1 meter is equals to what? 100 centimeters. Okay, so I'm going to say times, and then since centimeter, I'm going to say times here, and then I'm going to draw a line. So since the centimeter is on top here, for it to disappear, it has to be down there. Okay, and then on top, I'm going to put a meter. And then I'm going to say, okay, 1 meter makes how many centimeters? 100. So this is the conversion factor here. This one here, okay, I've written it in that form to cancel out the centimeter. Okay, if I had a meter on top here, it means the meter would have gone down, so even the one will fall. So it will be 1 meter is equivalent to 100 centimeters on top here. Okay, but here since we have the centimeter on top, we have to put it down. Okay, so even its value will fall down there. Okay, so now this is for the centimeter. So we are remaining with the seconds. Okay, so these seconds here, we want to convert them to hours like that. So we're going to say multiplied by, you draw a line again. Okay, so since this second is on top there, I mean, it's below there. Here we're going to put it on top. Okay, so how many seconds make up an hour? Okay, so 1 hour is equivalent to 300 and 3,600 seconds like that. Okay, so I'm going to put 3,600 seconds on top here so that this second and this second can cancel. Okay, and then down, I'm going to say 1 hour. Okay, so 1 hour is made up of 3,600 seconds. Okay, and then from here, um, we can do the multiplication. Okay, we can do the multiplication. So let's do the multiplication to see what we are going to have. So on top here, it will be 100 centimeters multiplied by 1 meter multiplied by 3,600 what? Seconds. Okay, so when I multiply that, what do I get? So 3600 multiplied by 1 multiplied by 100. Okay, so I'm going to get 360,000, and then I put the unit centimeter multiplied by the meter multiplied by the second. And then down there, what are we going to get? We have 1 multiplied by 100 multiplied by 1. So here we're just going to get 100, okay? And then I have the second multiplied by centimeter multiplied by the hour. So now you see the magic that the units that we don't want, they're going to cancel out, okay? So I can see centimeter and centimeter will go. This second and this second will go. So I just remain with this number here and meters per what? Per hour. Okay, so that's what we wanted. So you can just cancel out the zero. So cancel 2 zeros here, even there cancel 2 zeros. So I'm going to remain with what? I'm going to remain with 3,600 and then meters there divided by 1 hour. Okay, which is the same as 3600 meters per hour. Okay, so we have converted this 100 centimeters per second to meters per what? Per hour. Okay, so that's how we can do that. All right, and then from here, let's look at question 3. So question 3, they're saying an average adult has 5.2 liters of blood. Okay, what is this volume in cubic meters? Okay, so here you just have to know the conversion factor. Okay, so um the conversion factor, okay, from cubic meters to liters is as follows. Okay, so the conversion factor says that 1 cubic a meter, okay, 1 cubic meter is the same as 1,000 liters, like this. Okay, so here now I have 5.2 liters. Okay, how many cubic meters am I going to have there? So you cross multiply. Okay, so when I cross multiply here, what am I going to get? I'm going to get 1 multiplied by 5.2. I just get 5.2, and then liters multiplied by cubic meter divided by, here I have x, okay, multiplied by this, which is 1,000 liters. So this is going to be equals to 1,000 liters x. Okay, maybe I should write it on top here. So what I have there was, when I multiply x multiplied by this, I'm just going to get 1000 liters multiplied by x is equals to this multiplied by this. I got 5.2, okay, liters multiplied by cubic meters, like that. Okay, so this is what we have. So from here, we want to find the value of this x. So I'm just going to say x is equals to, so I divide by 1000 on both sides. So this would be 5.2 liters and then cubic meter divided by 1000 liters. So you see that the liter cancels, even here it cancels. Okay, so I have 5.2 divided by 1000. Okay, so you just punch that on your calculator. Okay, so my calculator says I get 0.0052 and then cubic meter, like that. Okay, so this goes to say that 5.2 liters of blood is the same as 0.0052 cubic meters. All right, so we're done with question 4. Let's look at we're done with question 3. Let's look at question 4. So question 4 is the simplest here. Okay, it's the simplest. So question 4, they're saying round off the following measurements as indicated. So A, okay, we have 0.9997654 meters. So they're telling us to round off this number to two significant figures. Okay, two significant figures. Okay, so what are we going to do? First of all, we can express this number in scientific notation, okay? Or we can round it off just the way it is. Okay, we can round it off just the way it is. So for us to round off, we want two significant figure. Okay, so if we start counting from here, how many significant figures we have? We have 1, 2, 3, 4, 5, 6, 7. So I want to cut these 7 significant figures to 2. So 1, 2. So the second one is here. So I'll draw a line here. So it means I'll have to round off this value to the next one. Okay, but when I round it off, notice what happens. Okay, so when I round off this 9, since this 9 is greater than 5, I should add a 1 to this 9. Okay, so when I add a 1 to this 9, I'll get 10. Okay, but I can't write the 10 here where there's 9. So I just write 0, and then this one goes to the next 9. Okay, but when I add that 1 to this 9 again, I'll get 10. So what do? Here I'll remain with 0, and then this one goes and adds to this 0. So what I have is 1.00, like that. Okay, but this here is not two significant figures. Okay, because these two zeros here, they will be significant because there's a presence of a decimal point. Okay, so it means I have to round it off again there. So this 0, it's less than 5, so I won't add anything to this 0. So the final answer there is to be 1.0. Okay, then this one here will have two significant figures. Okay, or if you want, you can actually express, first of all, this number, you can express it in scientific notation. Okay, you can express it in scientific notation. So what we can do here is this. We can say, let's take this decimal place one step to the right. So this will be 1.997654 times 10, okay, to the power. How many times have I moved? I've moved one time to the right. So if you move to the right, then it means the power there should be negative. Okay, so they are opposite. You move to the right, power here should be negative. Move to the left, power should be positive. So I've moved to the right one step. So I'm going to say -1 there. Okay, and then I have now to round off this number here so that I only have what? Two significant figure. So I'm going to round it off from there. Okay, I'm going to round it off from there. So when I round off this 9 here to this, since this 9 is greater than 5, I'll add the 1 here, which will give me 10. But I can't write the 10 here. So I'll just write 0 here, and then the 1 goes here. Okay, so when the 1 goes there, what am I going to have? I'm going to have 10 here. So I can write the 10 there because this is just a 9. So it will be 10, okay, 0.0 times 10 to the power -1, but I still need two significant figure. So I can move this decimal place one time here. Okay, can move this decimal place one time there. Or okay, or I can just ignore this 0.0 here because this one is making this number to have two significant figures. Or I can just write it 10 times 10 to the power minus 1. Okay, so this one here, okay, I've forgotten a point. I can just write it 10 point times 10 to the power minus 1. So this one here is also two significant figures. Or the first one that I wrote was 1.0. So you can express it as 1.0, two significant figures, okay? Or 10 point, don't forget this point here because it's the one that makes this 0 significant. So 10 point and then times 10 to the power minus 1 also gives us two significant figures, okay? So don't forget to add the units even there. So you can write your answer like this, or you can write the answer like this if you like scientific notation. Okay, then let's look at B. So B, it will be very simple because we've done the same on A. So B, we have 999.99876 meters. So they want us to put it to three significant figures. Okay, so this is 1, 2, 3. So I'll round it off from here. So if I round off this 9, this is going to become 10. So I'll just write 0 here, and then I take the 1 to this point. So this also becomes 10. So I'll just write 0 here, and then I take this one to this point, which also becomes what? It also becomes 10, this one. So the last one can become 10. So I'll write the last one has become 10. Here, I'll just write 0. Here, I'll just write what? 0 like that. Okay, but how many significant figures does this number have? It only has one. Okay, it only has one because this one here is the one which is significant. Okay, so how do we make it to have three significant what figures? Okay, how do we make it to have three significant figures, but we don't change the meaning? Okay, so we can actually express this number in scientific form, okay, or we can just manipulate it in another way. Okay, but the simplest here is scientific form. So when I write 1000 like this, okay, it means here at the end I have the decimal point. So I can use this decimal point, okay, to make this number have three significant figures. So what am I going to do? Okay, what am I going to do? I'm going to say, let's move this point one place to the left. So this number here becomes 100, okay, becomes 100, and then times 10 to the power. So I've moved how many times to the left? I've moved 1 like that. So this becomes 10 to the power 1. Okay. And then how do I make this here have three significant figures? I add the point there. Okay. So I've just moved this point here to this point. So this is the point that I'm talking about. Okay. So 100 point times 10 to the power 1 meters. This number here has 1, 2, 3 significant figures. Why is it 3? Because there's this point here. So if there's a presence of a decimal point, then the trailing zeros, which are this one and this one, they'll be counted as what? Significant. All right, so that's what we can do there. Otherwise, we move to question 5. So question 5, was what I was teaching you guys on Wednesday. Okay. I was teaching you guys on Wednesday. So this is on uncertainty. So if you didn't watch that video, please go back and watch it because it will give you all the details, okay, that you are supposed to know when answering such questions. Okay, so here they're saying the concentration of copper in soil sample was recorded as 270 parts per million, okay, of copper. Okay, so the first question they're saying indicate the certain and uncertain digits in the above measurements. Okay, so we said the uncertain digit is always the last significant number, okay, or the last significant digit in a number. So this number here, how many significant figures does it have? It has two significant figures. Okay, why? It's just this 2 and this 7 here. This 0 is not significant here because it's a trading 0 and there's no decimal point here. Okay, so we have two significant figures. So the first significant figure is the 2, the last one is the 7. So the last significant digit is always the uncertain digit. Okay, so we are going to say uncertain digit. Okay, the uncertain digit is actually the last significant figure, which is what? 7. So 7 is the uncertain digit. Okay, and then what is the certain digit? So the certain digit is the 2, this one here. Okay, the one that comes after. I mean that the one that comes before the uncertain digit. Okay, it can be one, like in this case we have 2, so it's the certain, or they can be more than 2. So if I wrote a number like 3450. Okay, this 5 here is uncertain because it's the last significant number in this number that we've been given. Okay, and then this 3 and 4, they'll be what? They'll be certain digits. Okay, so always look out for the decimal point there because sometimes they can just write it as 3, or let me use the same one, this one here. They can just write it as 270 point parts per million. So when they add this decimal point here, it means this 0 now has become significant because it's a trading 0 and there's a presence of a decimal point. Okay, so in this case, we would say the uncertain digit will be 0 here. Why? Because it will be the last significant digit in this number here. Okay, but in our case here, that the way it has been given here, the uncertain digit is the 7, the certain digit is the what? Is the 2. Okay, so now that we've indicated the certain and the uncertain digit, it will help us find the uncertainty. Okay, so how do we find the uncertainty? We said we play with the abacus. So the abacus, if you remember, it had ones, tens, hundreds, and then thousands there. Okay, so this number here, the way it is, it's 270 because we read this as 270, right? So meaning the 2 is in the hundreds, the 7 is in the tens, and then this 0 is in the ones like that. Okay, so the uncertainty is dependent, okay, on where the uncertain digit is on the abacus. Okay, so the uncertain digit here is in the tens. So it means the uncertainty, okay, the uncertainty is equals to plus or minus 10. Why? Because this uncertain digit is in the tens there. Okay, if it was in the ones, the uncertainty would be plus or minus 1. If it's in the hundreds here, it will be plus or minus 100. If it is in the thousands here, it will be plus or minus 1000. Okay, and then after the ones, what we have here are tens here, tens. So in the tens, the uncertainty will just be 0.1. So it will be plus or minus 1. Okay, that is if the uncertain digit comes after the decimal point here. Okay, so if you didn't watch that video, please go back and then you understand more. Okay, so just search uncertainty to solution. It's going to come. So here, since this 7 is in the tens, our uncertainty will just be plus or minus 10. Okay, so now that we have our uncertainty, we can determine the higher reading, the lower reading, and the range. So we're going to say the higher reading is just going to be equals to, okay, 270 plus 10. So this will be 280 parts per million. And then what will be the lower reading? So lower reading will just be 270 minus 10. Okay, so this will give me 260 parts per million. Okay, and then what about the range now? Okay, so the range of uncertainty will just be equals to the higher reading, which is 280 minus 260. So we are going to get what? 20 parts per million. So this is the range of the uncertainty. All right, so we are done with question 5. Let's look at question 6. So question 6, they're saying an analyst made measurements with percentage error, okay, percentage error of 2.1%. The average of measured values, okay, was 28.13 milligrams. Okay, so the average of a measured value, simply meaning the measured value, okay, or the recorded value. So the recorded value or the measured value was simply 28.13 milligrams. And then they're asking us to find the true value or the actual value. So how can we find it? Okay, we just use the formula for percentage error. So we know that percentage error is actually equals to, okay, it's actually equals to um, the measured value, okay, minus the true value, okay, and then you get the modulus of this. So it doesn't matter if it gives you a negative or a positive, it will still be a positive because we have a modulus, and then divided by the true value. Okay, so this is the formula for the percentage error. Okay, so from this formula now, we're just going to put these numbers here. Okay, we're just going to put these numbers here. All right, so I've forgotten the 100 here. So you multiply by the 100 because the percentage, right? Okay, so here we have the percentage error being 2.1 multiplied by, okay, at 2.1, I mean, is equals to modulus. So the measured value is 28.13 minus the true value. So the true value, we don't know. We want to calculate it divided by the true value, okay, which is just TV multiplied by 100. Okay, so from here, what are we going to get? Okay, so here we can remove the modulus and then we can cross multiply. Okay, we can remove the modulus and then we cross multiply. So what we're going to have is that we're going to have 2.1 is equals to 28.13, okay, 28.13, and then minus true value multiplied by 100, and then divide everything by the true value. So now we can cross multiply. So cross multiply, we get 2.1 TV is equals to, and then here we multiply this 100 multiplied by this, and then this 100 again multiplied by this. So what do we get? Okay, we get we get okay, we get okay, or maybe we can try to divide to avoid getting bigger numbers here. So we can say let's divide both sides by 100. Okay, so if I divide this side by 100, it's going to cancel out with this one. If I divide this side by 100, what do I get? Okay, so here I'll just say divide by 100, and then there I remain with 28.13 minus TV over TV. Okay, all right, so when I, oh, this TV, I cross multiplied it, so it's there. So here it's not there like that. Okay, I cross multiplied there with this. So this one here, when we divide it, it will be 0 point to be 0.021 TV is equals to 28.13 minus TV. And then let's put the like terms together. Okay, let's put the like terms together. So what are we going to have there if we put the like terms together? Okay, so if we put the like terms together, it means the TV will come this side. So I have 0.021 TV plus the TV, which is just the same as 1 TV, right, is equals to 28.13. So let's add those. Okay, so when we add them, what do we get? We get 1.021 TV is equals to 28.13. And then we divide by 1.021. Even there, we divide by 1.021. Okay, so what do we get there? So just punch whatever I've written there onto your calculator. So this one and this one goes. So I have TV is equals to 28.13 divided by 1.021. I get 27, according to my calculator. Please confirm. 27.56, and this was milligrams, so it means if even the true value is in what? Milligrams. Okay, and then also take note of the significant figures there. Okay, take note of the significant figures. All right, so this here will be our true value. Okay, that will be our true value. All right, so we are done with this one. Let's look at our last question, which is on accuracy, precision, and then the type of errors. Okay, so um, before we even solve the question, okay, we have to understand what accuracy is and what precision is. Okay, so what is accuracy? Okay, we start with accuracy. Okay, so accuracy simply means that or simply refers to how close, okay, a measured value or a recorded value is to the true value or the actual value. Okay, so how close a measured value or recorded value, okay, is to the true value or the actual value. Okay, so this is accuracy. So, for example, if my actual weight of something is uh, let me say 5 grams. Okay. And then I take these 5 grams, I measure it on a weighing balance, and then I get 4.99 grams. Okay. So this 4.99 grams is very close to this. So we're going to say that this measurement here is what? Accurate. Because it's closer to the what? To the true value. Okay. But what if I measured this 5 kg and then I got a 3.9 gram? Okay, so if I got the 3.9 gram, it means this 3.9 grams is not close to the 5 grams, which is the true value, right? So we are going to say that this measurement here, the 3.9, is not accurate, okay, because it's not close to the true value, okay? All right, so now that is what accuracy is. And then let's talk about precision, okay? So precision, okay, precision refers to, okay, how close repeated measurements are to each other and not necessarily close to the what? To the true value. Okay, repeated measurements are to each other. Okay, so how close the repeated measurements are to each other, that's what we call precision. So the recordings, okay, or the measured values may not be necessarily close to the true value, but if they are closer to each other, then we are going to say they are precise. So if my actual value is 5 kg, and then I have a series of repeated measurements. Let's say 2.5. When I put this on the balance, I also get maybe 2.6 grams. I get 2.4 grams. So we see that the measured values here are not anywhere near the true value. Okay, but they are closer to each other. So we're going to say these measurements here are what? Precise. Okay, but are these measurements accurate? No, because they are far away from the true value. But they are precise because they are closer to each other. So precision will be looking at how close the repeated measurements are to each other, not necessarily to the true value. And then the true value, okay, I mean the accuracy will be looking at how close the measurements are to the what? To the true value. So that's what we mean there. Okay, so now if you're given more than one, okay, if you're given more than one measurements and then you want to determine the accuracy, what you have to do there, okay, is to find the average of whatever measurements you've been given. Okay, that's when you can tell if they're accurate or they are not. Okay, otherwise you can't just get the individual measurements and then you compare them to a true value. No. Okay. So you find the average and then you compare the average to the true value. That's when you can say that those measurements they are either accurate or precise. Okay. All right. So let's comment now. Okay, on the student A, B, C, and D. Okay, are they accurate? Are they precise or they are not? So we start with the student A. So I'm just going to write A here, meaning student A. So student A has 34.6 grams, 34.5 grams, 34.7, 34.8, 6 grams there. Okay, so and then here down there, we've been told that the true value is 25.0 grams. Okay, so we start with the accuracy. So I'll say 1 here. Okay, so how is the accuracy of this? Okay, so here they're saying comment high or low on each student. So the accuracy here is actually very low. Okay, because the true value is 25 grams. But when you're putting this thing on the weighing balance, it's giving you 34.6. So meaning the accuracy there is low. Okay, so these measurements here are not accurate because they are far away from the true value there. So we're going to say for the accuracy here, we're going to say it's what? It's low. What about the precision? Okay, so the precision, we can see that these measurements here, even though they are not close to the true value, they're actually very close to themselves. So we're going to say the precision there is high. Okay, student B. So student B, let's look at the measurements. Okay, so we have 4.36, 4.35, 4.37, 4.36. So we see that again, when we talk about the accuracy there, the accuracy is very low. Okay, why? Because these 4 point somethings, they are very far away from the 25, guys. Okay, and then what about the precision? Okay, we see that they are close to each other like that. So if they are close to each other, then we're going to say the precision is what? Is high. Okay, what about the student C? Okay, what about student C? So student C, we have okay, student C, we have 24.9, 25.1, 25.0, 24.9. Okay, so at these measurements here, closer to the true value, okay, we see that they're what? They're close because the true value is 25. This is 24.9, 25.1. So we are going to say that in this case, the accuracy is high. Those measurements are accurate. What about the precision? Okay, so the precision here again it will be high because the measurements are closer to each other. So we are going to say even the precision is what? Is high. Okay, so now we are just remaining with student D. Okay, so let's check what we have on student D. So student D, we have 64.6, 35, 34.5, I mean, 14.7, and then 10.8. Okay, so are these measurements accurate? No, they are not close to the true value. So we're going to say the accuracy there for student D is actually low. What about the precision? Okay, so the precision there, you can see we have 64, 34, 14, 10. Okay, so there's no preciseness there. Okay, so the precision here on student D is also low because these numbers here, they're not closer to each other. Okay, they're not closer to each other. So we have determined, okay, on each measurement, whether they're accurate or what? Precise. So this was the part A. Okay, now part B will be to determine what type of error affected these measurements. Okay, all right, so B, they're saying comment on the type of error that affected the measurements for each student. So the type of errors that we have, okay, we have one, the systematic error, okay, we have the systematic error, and then two, we have the random errors. Okay, so the way these things happened is that the systematic error have a direction, while the random error does not. Okay, so if, for example, my true value is 10, right? This is my true value. So for the measurements to be affected by systematic error, it means that all those measurements should either be lower than the true value or they should be greater than the true value. So let's say, for example, I got some measurements for the true value of 10, and then I get 15, 16, 17, okay, 19. We can see that all these measurements here are greater than 10. So they are in one direction. Okay, so the error is in one direction like that. We're going to say that is systematic error. Okay, another set of data can be that maybe I get 2, okay, 2.5, 3, 4, as my measurements, okay, and my true value is 10. So since all of them they are below the 10, we are going to say that's systematic error because they have a direction. All of them are going below the 10, okay? All right, and then for random errors to occur, it means we have no direction, okay? The error is happening in both the increasing and the reducing direction. So if my true value is 10, for these measurements to be affected by the random error, it means when I measure this object on my weighing balance, some measurements will be lower than 10, others will be higher than 10. So maybe I get 3, 4.5, okay? And then I also get 16, 20. We can see that of the measurements that I got, some of them are below the true value. Some of them are above the true value. So there's no direction here because my error is going to the right. It's also going to the left. So the random errors have no direction, while the systematic ones have the direction. So the systematic will happen in one direction. It's either those measurements are all greater than the true value, okay, or they are all less than the true value. But for the random ones, okay, the measurements will some will be greater than, some will be less than the what? The true value. Okay, so now we've known the concepts. Let's comment on each of these measurements here. Okay, in comparison to the what? To the true value. So the true value here is 25. And then on student A, we can see that all the measurements here are greater than 25, right? So we're going to say here the error is a systematic error. Okay. B, all the measurements are less than the true value. So that will be systematic error again. Okay, and then C, okay, these errors here, okay, are they in one direction or they're in both direction? Okay, so the true value is 25. Okay, the true value is 25. Uh, and then we have 24.9, which is a value that is below 25. We have 25.1, which is a value above. Okay, so in this C here, though there is minimal error, minimal, it means this is the perfect measurements, okay, because these values here are all close to this one. Okay, so there's high precision, there's higher what? Accuracy. So there's minimal error there. But what type of this same minimal error? Because it's up and down, we have some measurements that are lower, okay, than the true value, and some that are greater than the true value. We're going to say here there's minimal error, and that error is what? Random. Okay, what about D? Okay, so D, we have measurements that are above the true value, like this 64 here and the 34 there, it's above the 25. And then we also have measurements that are below this 25, which is 14 and 10. So we're going to say this one is affected by what? By random errors like that. All right, so we are done with this tutorial sheet. Okay, so whenever you are given a tutorial sheet, please be sending it in the group and then we'll make a video for it. Then we'll upload it on our website. Okay, so you can find a lot of things on our website. You can learn at your own time, anywhere, even in your blankets, you can learn. All right, so that's all for this video until we meet next time.